Okay, and welcome back to our part two of how voltage and current behave in parallel. So when we wire things in parallel. Again, we don't really want to say in a parallel circuit. We just want to say when things are wired in parallel to each other. Because in the real world, most circuits are complex combinations of series and parallel. But for right now, to just establish the rules, we're looking at things just wired together in series, or in this case, just wired in parallel. And to recap from the last video, we saw that the rules for how voltage and current behave in parallel are the opposite of series. Now, instead of sharing a total voltage, they share a total current. And instead of the current being the same through all things in series, the voltage is the same thing across all things in parallel. We're applying 6 volts, so 6 volts goes to this one, 6 volts goes to this one, and 6 volts goes to this one. Now, just like we saw in series, the voltage is shared, but it's shared proportionally. When things have the same resistance, well then yeah, they all get the same amount of voltage. So the same thing's going to kind of happen here. They're going to share the total current, but that's not necessarily going to be the same amount based on how much resistance we have in each branch. So right now we've got our same setup from last time, our 3 identical bulbs, but now we're going to try it with our 10 ohm resistor, our 50 ohm resistor, and our 100 ohm resistor, and we'll see what happens. So we will disconnect. We'll get these light bulbs out of the way. And now we'll just hook up each one to see about how much resistance we're going to get. And now I'll try to dial this back down to the 6.1. Let's see if we can dial that in real nice and neat. So we've got about, actually clip on. So 6 volts, 10 ohms, 0.6 amps. Ta-da! Now let's unlock that one. Now we've got 6 volts, 50 ohms. How much current? Were you right? I don't know. Let's see. So now we've got 0.12, right? So 5 times as much resistance. What do we notice about how much current? So what's this divided by 5? Oh, you tell me 0.6 divided by 5 is 0.12? Interesting. And now we've got a 100 ohm resistor, right? So remembering that this was 0.6 amps, if you've got 10 times as much resistance, you're going to get, hopefully, 10 times less the current, so 0.06 maybe? Ta-da! Awesome. So, what we can see is that, though, that's how much current there would be in each one. But what we can do now is we can put this here. So this is 0.6 amps of current. Now we measure this one to be 0.12. So if we put them together, we see that they do add up, right? The 0.6 plus the 0.12 is giving us about 0.72. It's a little bit more. We can kind of fine tune that down if we wanted to, because these things are rounding off a little bit. There we go. Oh, come on. Nope, hold down. 0.74, 0.73, 0.72. Oh. There we go. Aha, there we go. Cool. So we get about 0.6 there. 4.59. There we go. And now we add this one, and we saw that this one was 0.06. So this should bring us up to about 0.78-ish, hopefully. Yeah, there we go. So the same rule applies, right? So we can measure across each one. Let's measure the voltage. As we can see, we got our handy dandy little voltmeter right here. So we measure this. We're getting the same 5.9 volts, right? We're supplying 5.9. We're getting 5.9. No, I got to work on my virtual pointing. 5.9, 5.9. 5.9, nothing because I just unplugged the thing. 5.9. Now, it says 5.9 here. Again, we're probably losing about 0.1 just to get there. So if we measure across these, let's see. Hey, why'd you turn off? There we go. Oh, that didn't go in. 5.8. So, or 5.9. 5.8, 5.9 is what we're supplying there. And that's what we get. So the same rules apply, right? So same voltage, same voltage, same voltage. We applied 6, each one gets 6. And the current still added up, even though it wasn't spread out equally, right? It wasn't just, 0.78 divided by 3. It was depending on the resistance, right? It's still Ohm's law, right? 6 volts and 10 ohms gives us 0.6 amps of current, which is a little bit hot. We're just getting a little bit hot, so we're going to unplug that for a minute from this wood table. And this one gave us 1.2 amps of current, or sorry, 0.12 amps of current. This one gave us 0.06. You add those up, and you get the full current here, right? 0.12 and 0.06, current still adds up. And that's basically it. This is probably the shortest video of all of them, but the same rules apply. The really nice thing is that they are opposites of each other. Right, so if you can memorize one of them, you've memorized the other one, and I don't know, that seems pretty helpful to me. But to sum up again, the way these things work is when you've got things wired together in series, like any number of things, they will have the same amount of current flowing through them, but they will share the total amount of voltage being applied to them. And when you've got things wired in parallel, it is the exact opposite. They will share the total amount of current, but they will automatically have the same amount of voltage. And to kind of sum that all up, what I've got is a nice, neat little chart here that I will make available to you. And we can show you what that's going to look like here. So let me see if that works. Let's see. We can shrink this down a little bit, and then we can bring this video up so we can test to see exactly how much we're getting there. And now we can minimize this. We can get it out of the way. And here's how it works, right? So we've got the voltage and current, and when they're wired in series, we know that voltage is going to be conserved. The circuit elements will share the total we apply, and we can kind of write that as an equation, right? So when things are wired in series, we know that the voltage supplied is going to be equal to the sum of their voltages. All right, so V supplied will equal voltage 1 plus voltage 2 plus voltage 3. They might be all equal, they might not be. That depends on their resistance. Right? Things with more resistance are going to get more of that voltage. And then in the current in series, they're just all equal. The current through each element is the same. And things with more resistance still get the same amount of current. The current through like resistor 1 will be the same thing as current through resistor 2 versus resistor 3. They all just get the same amount of current. Now in parallel, it's a little bit different. In fact, it's the exact opposite. Branches wired in parallel all get equal voltage. Just no matter what. Whatever they're being supplied, they all get equal amounts. But the branches, their currents will add up to the total current being supplied to where those branches break off from. And again here, it does not matter. Things with more resistance, they all still get the same amount of voltage. As we saw, the 10 ohm resistor got the same voltage as the 50 ohm, is the same as the 100. Because we're hooking them up in independent paths. So parallel is kind of like independent. Right? It's divided into separate branches or separate paths of current. And they'll just all get equal amounts of voltage. But their currents will add up. The currents through parallel branches will add up to the total amount of current being supplied to that branch. And again, you don't have to worry about trying to copy this all down. I'll put both a blank one and a filled out one onto Schoology for you. So if you want to download it, you can print it out, you can write it out. You know me, I'm a firm believer in the connection between handwriting things and you remembering them. So I would highly recommend doing that. But if you just want to have this, you can open it up and use it to check out any of the practice problems we do. We'll focus on those next week, but this is what's going to hopefully help you crack the circuit this week. So hopefully you found that helpful, and good luck on all your future endeavors.